So now we're ready to talk about cardinality in general, um, just as a bit of terminology here. So two finite sets. So two finite sets have the same cardinality if they have the same number of elements. So again, if they have the same number of elements in them. So if you have two sets both with 5 elements, we say that they have the same cardinality. So if they have the same number of elements. Again, I'm really repeating myself here. We've already said that. If two sets have the same number of elements, then they have the same cardinality. That's kind of how we define cardinality to begin with. But there's a reason why I want to revisit this. So we're going to say a set is countable or countably infinite. So a set is countable if it has the same cardinality as the non-negative integers. You notice that I could put whatever set I want here. I could actually put that a set is countable if it has the same cardinality as the integers. And when I say the same cardinality, just to be clear, what I mean by the same cardinality is that there exists a bijection between the set that we're talking about and the non-negative integers. Okay, so that's what it means to be countable. So there's a bijection between that set and the non-negative integers. And again, I need to write this just a little bit better here. This is the non-negative integers n, so just to make that a little bit more legible. Okay, so it's a bold n. Okay, so to be countable means that there's a bijection from the set to the non-negative integers n. And again, there's nothing special about n. You could pick any of the previous sets that we talked about. You could pick the integers themselves, the even integers, the positive even integers. Think about what we know about bijections. We know that if we have two bijections, we can compose them to get a third bijection. So the composition of a bijection with a bijection is another bijection. So what that means is that if you can find a bijection from the natural numbers to some set, and then there's another bijection from the natural numbers to a third set, so if you can find a bijection from some set to n, and then a bijection from n to the set, then there's also a bijection from the first set to the last set. So there's really nothing special about n. It's just a nice convenient way to state this. So a set is called countable if that set has the same cardinality as the non-negative integers. In other words, if there exists a bijection between the non-negative integers and that underlying set. Now, very surprisingly, it turns out that if you look at an interval of real numbers from 0 to 1, this is not countable. Okay, this should be weird. This should bother you. This says that not all infinite sets are the same. In a certain sense, there's a different number of elements in the non-negative integers. So the infinity that goes from 0, 1, 2, 3, 4, and so on. So people call that the number of seconds and forever, is different than the set of real numbers from 0 to 1. Even though both have infinitely many elements, in a certain sense, the set from 0 to 1 has way more stuff in it than there are integers from 0 to infinity. Okay, so what we're going to do is we're going to prove this in the next video. The set from 0 to 1 is not countable.